So we're here to look at some torque. Okay, so what we're looking at is torque. Um, and torque can be thought of as a turning force on an object. So if you've ever had a wrench that you've been, twisting a bolt into place or a nut on a bolt, a screwdriver is applying a torque to the screw head. Whenever you turn the top on or off of a pickle jar, like you're applying a torque. It's a rotational force to an object. Um, and the torque is dependent on three things here. If we kind of look at this monkey wrench, if you imagine tightening some bolt onto something, the torque is dependent on just how much force are you applying. Are you using all of your muscles to crank something into place, or are you just poking it very gently? So it depends on the amount of force. It also depends on what's known as a position vector, also known as a moment arm of this. If you've ever actually used like a big wrench here, if we imagine that we're pivoting around this point right here, kind of the bolt, if you have a very short wrench here, then you have what's known as a very short position vector or a short moment arm. If you ever find that you're trying to like free up a bolt and you just can't, then you might use what's known commonly as a breaker bar, or it's a very, very long wrench. And the reason being is that whenever you do this, you get a much, much longer position vector or moment arm. And you can either tighten something much greater or much easier, or remove something much easier because you've got this larger moment arm or this position vector. And the last thing that matters is the angle between the force and the position vector. Are you pulling this wrench straight backwards, or are you pulling it at some angle? Because if you go to try to push it like this, you're not really going to do anything. And a common way to think about this other than wrenches are doorways. If we think about a door, let's see if I can draw a decent door here. Here's a door. Here are the hinges on the side. And here's a nice little doorknob. We always put the doorknobs on doors on the outer edge here. And the reason we do that is if these hinges are the axis of rotation, we measure the moment arm away from those hinges to the doorknob. By having that larger moment arm, it's easier to open the door. You can apply more torque. If you were to take your fingers and put them right in the door jamb, or like right on the edge of the hinge there, and try to open up a door, it's going to be very difficult to open up most doors. So we open them from the outside. The other thing that just affects opening the doors are you kicking the door with like a huge force, or are you just gently pushing it open? And last but not least, the angle here, we keep opening the doors by pushing this way. Nobody opens a door by pushing into the door, like into the jamb. That doesn't even make sense. That you're like trying to push it into the wall. What's going on? And if you try to pull away from a door like this, you'd be trying to pull it off of the hinges somehow, which that doesn't rotate the door. It doesn't cause the door to, open or close. That's just literally removing the door. So if we think about doors, these same kind of ideas apply here for a turning effect or a torque. Mathematically, we think about the torque as a cross product, which if you've seen the previous video on cross products, take a look at that, Corona video 6.5. But it is the cross product of a position vector, this moment arm, this r, this radial distance, and the applied force F with that cross product. Now, since it is a cross product, this is where our angle comes into play. The torque equation can be thought of then as a radial distance, that moment arm, crossed with the force vector. And since this is crossed with the force vector, what we can say is it can really be thought of as the magnitude, or just the size of that moment arm, multiplied by just the magnitude or the size of the force times the sine of theta, or the angle which is between these two vectors here. Now, oftentimes when we think about this, if we look at our door from the top down, people often make the mistake of saying, hey, look, I'm pushing at the door out here, and my moment arm is like this. Or maybe we'll push the door. Let's push the door like this. And my moment arm is the pink one here. So this is our force, and this is our moment arm. You know, maybe this is the angle I'd want to use. That's not the case. Whenever we think about torques, what is easier to do for our right-hand rule in finding directions of these torques is to take a vector such as the orange one here and slide it to the pivot point. Okay? Yes, I know it is acting all the way out here, but when we look at our angles, it's going to be easy to think about this as from the pivot point. So when we do this, since it is R cross F, and let's bring us, let's call this some force over here. This is our force. Since it's R cross F, we are looking for the angle from the moment arm to that force. Now, the angle looks the same, and it is the same mathematically, but it's easier to think about the direction of the torque when we do this. The reason why this matters is when you're doing the right-hand rule, it's called the right-hand rule for a reason. You use your right hand to do it. We think about this as placing our fingers in the direction of the first vector, which in our case here is going to be that moment arm, and we curl our fingers in the shortest angle possible to get to that second vector, the force. So we curl to that force. And when we do this, you know, if I'm looking at my screen right here and I go from R to F, I can see that my thumb is pointing either out of the screen, or if I'm doing this on paper in front of me, it's pointing out of the paper in front of me. It's like going up towards the ceiling. And since this torque is based off of the right-hand rule, where the thumb is pointing is the direction of the torque, which is a little bit weird to think about, but that means in this case, the torque is pointing out of the page. And we draw out of the page as a circle with a dot on it. You can imagine it as an arrow coming towards you. If things were into the page, which they're not in this case, but into the page is a circle with an X on it, we can think of as the X as being like you're Robin Hood and you're drawing back a bow and you've got the little feathers here, the fletchings, and whenever you fire it, the fletchings go into the page. But that's one way we can think about the torque vector. The other way to think about it, if you're like, Botzer, I don't want to move vectors around, then what you can do here is if you think about how this force is pushing on the door here, this door will rotate in this direction, the counterclockwise direction, what we call positive. And if it's rotating that counterclockwise direction, if you just curl your fingers in that counterclockwise direction, the direction your thumb is pointing will give you the same thing. So that's two ways to take a look at that right-hand rule. So one of the things that we're going to discover in class is most of the time we are going to have our force to be perpendicular to the position vector. That's just how you open doors traditionally. And when that's the case, our angle here is going to be 90 degrees. It doesn't have to be this case, but it makes a lot of problems easier. What makes problems so easy is that whenever your sine is 90 degrees, it is equal to 1, which means whenever force is perpendicular to the torque, or to the moment arm, the torque is just going to be the moment arm multiplied by the force. Okay, so these equations right here, R cross F, or RF sine theta, and this are going to be super useful to us. One other thing that we're going to see is just like in F equals ma, this torque is the rotating force. So what we are also able to say here is while this torque is based off of a moment arm and a force, this torque can also be equal to I alpha. It's like a mass, that rotational inertia, and its angular acceleration. So this equation here, torque equals I alpha, looks a lot like F equals ma, which is something we're familiar with from earlier in the year. So if we take a look at a little example here, we have this bicycle wheel, and if you've ever been to a bike shop, you'll see bikes turned upside down all the time because they're repairing them. And what we know here is that when the pedal is turned, the chain So right here we have some sort of circular disc on the back end. And the chain, whenever it's tugging on this, is generating 56 newtons of force when it's on the gear there. We know the radius of those gears from the center out is 0.085. So this 0.085 here, this is our moment arm, R, and these 56 newtons, that's our force there, F. So if we think about this from the right-hand rule, I can imagine how this bike wheel is going to spin. That means my torque is kind of going into the page here. I can see that my R and F values are perpendicular from each other. What we can also do is we need to figure out the wheel's moment of inertia. We know the wheel has a mass of 1.7 kilogram of a thin ring. And a thin ring, if we go check our best friend, it has a moment of inertia of, I think it's 112, but let's check. Let's check it out. Where's a thin ring here? A thin ring or thin hoop? Oh no, it's just mr squared. Okay, that's fine. So it's going to be just the mass times the radius squared for that moment of inertia, and it has a radius of 0.65. So this radius is 0.65 for the wheel itself. So to find the wheel's moment of inertia, we do just say I equals mr squared for the wheel. That is the 1.7 kilograms times the radius of the wheel of 0.65 meters. Don't forget that squared. Let's multiply it all together real quick. So 0.65 squared times 1.7. We get a moment of inertia of about 0.72 kilograms meters squared. To find the applied torque, we know torque is going to equal R cross F, and in this case it's just going to equal RF because these moment arm and force vector are 90 degrees from each other, so the sine 90 is going to equal 1. So R times F is all we need here. For our two values, that's the 0.085 times the 56 for the force. It's going to give us 4 let's just round up to 8. And our units there are going to be newtons for force times meters, or newton meters. To find the angular acceleration of the wheel, we're looking for an alpha. And what we can do is we can say if torque equals the moment of inertia times the angular acceleration, well, we know a torque, we know the moment of inertia. Let's just combo this up. We can say 4.8 newton meters equals 0.72 kilograms meters squared times the angular acceleration. So on each side, we'll just divide by that 0.72. So 4.8 divided by 0.72 equals, the number of physics. We find an alpha here to be about 6.66 repeating. And those units are in accelerations, so they're going to be per second squared, but they're not going to be meters here because we're talking about rotation, so we're going to be in radians, or our placeholder unit. So that's how we can do a little bit of combining torques and rotational moments to find an angular acceleration. And this idea of a torque, it's pretty straightforward here. It's just how far away you are that moment arm from your pivot point, how much force are you applying, and is there an angle between things. Just keeping in mind how we calculate that angle, going from the radial position to the force vector, and our little right-hand rules for the torques there. Okay, so with that, that should give you a good idea of torque, and we'll be able to do some problems with that. Take it easy.